EAA's webinars are made possible through the generous support of Aircraft Spruce and Specialty, serving homebuilders and EAA members since 1965. Tonight's presentation titled Making Metal Behave. Our presenter, Mike Bush. Mike is president of Savvy Aircraft Maintenance Management, author for numerous aviation publications, CFI, A&P Mechanic with the inspection authorization, Aviation Maintenance Technician of the Year in 2008, and a member of EAA. Mike, thanks for being with us tonight. I'm going to turn control of the presentation over to you.
Well, great. Good evening, Tim, and good evening, everybody. As Tim mentioned, the title of tonight's presentation is Making Metal Behave. A while back, I did another webinar on metallurgy. I believe it was called When Metal Lets Us Down, and I talked a lot about fatigue and the way metal fails and so on. Today, we're going to be talking about metallurgy, some more metallurgy, but this time it's going to be a little less pessimistic. We're going to be talking about all the tricks that can be used to make metal have the characteristics that we need when we're using it to build pieces of airplanes. And I find this a very interesting subject. I hope you do too. We're going to be getting a little down in the weeds a few times as we go through this, but hopefully everybody will be able to hang on. No equations, I promise you. Metal is really cool stuff. It has a lot of characteristics that make it extremely useful. It's strong, it's hard, it's tough. We'll talk a little bit more about what those terms mean in detail as we go. It's easy to form, work, shape, machine. It's fireproof. It withstands high temperatures, especially certain alloys like stainless steel. It conducts electricity well. So in a lot of metal airplanes, we use it as a ground return for the electrical system. It conducts heat well. So it's good for heat sinking things, metal cylinder head fins, that sort of thing. None of these nice properties that metal has are unique to metal. There are a lot of other materials that have those kinds of properties. For example, just plain cotton fiber actually has higher tensile strength than the 2024 aluminum alloy that we use primarily to build airplanes. And Kevlar is one of the strongest things imaginable. Kevlar has significantly higher tensile strength than even the strongest steels. That's why we make bulletproof vests out of them. Diamonds and carbides, which are artificial diamonds, are harder than even the hardest metals. Ceramics can withstand higher heat than even the most exotic high-temperature metal alloys like Inconel. Wood is easy to shape and machine, so metal doesn't have a monopoly on that characteristic. But the thing that makes metal so useful is that it exhibits all of these properties at once. So it may not be the best at any particular thing, but it sure does a lot of things well. I like to think of metal as kind of the Cessna 182 or the Piper Dakota of the materials fleet. It does a lot of things well. Now, the thing that primarily sets metal apart from other materials is the way it reacts when you apply a force to it, the way it deforms. And all materials deform when you apply force to it, but the characteristics of how metal deforms is pretty unique compared to other materials that we use. And to understand this a little better, and I'm sort of heading a little bit into the weeds here, but I'm going to introduce a couple of terms that are used by metallurgists called stress and strain. When we apply a force to a material, the force we apply is called stress. It's typically measured in units, something like pounds per square inch or something. And the amount that the material deforms in response to that stress is called strain. And that's normally measured in terms of what percentage dimensional change the material has in response to the stress being applied to it. Now, you can apply stress in lots of different ways. You can just apply it in tension, where you're trying to pull the material apart. You can apply it in compression, when you're trying to squeeze it together. You can apply it in shear, in twist or torsion. But for the moment, we'll just talk about what material does when you apply stress to it in tension. That is, you're trying to pull the material apart, as it kind of shows in this picture here. And if we do that, if we put it up on a bench and we apply progressively more force to the material, more and more stress, and we measure how much it deforms at each value of increasing stress, we can draw a graph of how the material responds to the stress in terms of how much it elongates, or how much strain that stress generates. And the curve looks, sort of vaguely like this. We'll look at some more realistic curves in a minute, but just generally speaking, we draw a curve that looks something like this. When you start applying stress to the material and it starts deforming, at first it deforms in a linear fashion. That is, the graph it starts out as a straight line. And the slope of that straight line is something called Young's modulus. And it's a measurement of how stiff or flexible the material is. So if the material is stiffer, then that curve, that slope is steeper. That is, that the material deforms less in response to the stress. If the material is more flexible, then the slope is more shallow, and the material deforms more in response to stress. So the slope of that linear part of the curve is called Young's modulus. It's a measure of stiffness. Now, at some point, as we continue to apply stress to the material, we reach something called a proportional limit. And above that level of stress, the material starts acting in a nonlinear fashion. And the reason it starts acting in nonlinear fashion is it's actually starting to, its structure is starting to fail. And so it starts elongating at a greater rate as we apply more stress. And eventually we'll get enough stress that the material can't stand anymore. And that's called its ultimate strength. And if we continue to apply more stress, then the material fractures. It just pulls apart. So that's kind of an oversimplified version of the stress and strain relationship. Now, the thing that makes metal unusual, and that makes metal act like metal, if you will, is the fact that it exhibits two different kinds of deformation, elastic deformation and plastic deformation. Elastic deformation, which is how it initially responds to stress, is reversible. That is, when you take the stress away, the material returns to its original size. If you put enough stress on metal, then the deformation becomes plastic, and that is, it's irreversible deformation. So if you take the force away, the material is permanently deformed and does not return to its original dimension. And these photographs of springs being stressed, if you will, and then overstressed I think is a pretty good indication of what I'm talking about, the difference between elastic deformation, or reversible, and plastic deformation, which is irreversible. And so if we look at the actual stress strain diagram for an actual piece of metal, it looks something like this. The first part of the curve, where the metal is still reacting in proportional fashion, and just a little bit further than that, is considered the elastic zone, where the metal hasn't, the structure of the metal hasn't been disturbed in a way that permanently deforms it. So if we take the stress away, the metal goes back to the same dimension that it was before. But if we go past that, past what's called the yield point, then the metal gets into the zone of plastic deformation or irreversible deformation. And it will start to stretch in a way that is permanent. When we let go, it doesn't go back. And then if we keep adding additional stress in the plastic region, eventually it will reach its ultimate strength and then rupture. Now, it's important to understand that this kind of characteristic of elastic deformation at low stresses and plastic deformation at high stresses is reasonably unique to metal. It's what makes metal act like metal. Not all materials do this. For example, if you consider, brittle materials like glass or brick or ceramic or concrete, their stress strain curve is almost entirely elastic. If you put stress on them to the point that they no longer can retain their dimensions, they typically shatter. They won't deform very much without fracturing. And glass is the most obvious example. If you push on a window, it'll deflect a little bit, and if you let go back to where it was. But if you push more than that a little bit, the window will shatter. And that's characteristic of brittle materials like glass. Pliable materials like putty and clay and things like that are almost entirely plastic. If you push on them, they don't spring back. They stay where, that when you deform them, they stay deformed. Metal is unusual in the fact that it has these two different kinds of deformation, elastic at low stresses and plastic at high stresses. And that's one of the things that makes metal really useful, because the fact that it is elastic at moderate stress makes it tough and resilient. The fact that it is plastic under high stress, first of all, allows it to bend rather than break, and second, makes it cold workable, so that we can make bends in it and cold form it in various ways to get it into the shape that we want. So this dual kind of deformation characteristic of metal it makes it very useful. Now, the elastic deformation character of metal sometimes is very obvious, like in springs or in like this spring steel landing gear. I'm not sure what kind of airplane this is. It's not a Cessna, but it's something with kind of a Whitman style gear, and we all can kind of visualize how that landing gear deforms under stress and then springs back to its original shape when the stress is removed. It's not so obvious that other kinds of metal, like a crankshaft or a connecting rod bolt, do the same thing, but they do. When we torque up a fastener, for example, we're actually stretching it a little bit. And certain bolts, most of the time, we torque them to a specified torque, but certain kinds of bolts, like a lot of connecting rod bolts on Lycomings, are actually tightened to stretch, where you actually measure the length of the bolt with a special micrometer, and then you tighten the nut until the bolt has stretched a particular amount. So all of these things actually undergo elastic deformation, although it's not nearly as obvious with a lot of these parts as it is with, say, a spring steel landing gear or a coiled spring or something. Let's get a little bit into the weeds again and talk about a little chemistry here. Here's the periodic table that everybody learned in chemistry class in high school. And we've divided it up into metals and nonmetals. Something like 2/3 of the elements are considered to be metals. They're on the left side. And the things on the right side of the chart are called nonmetals. And that's a little bit oversimplified because the elements that are right along that boundary between metals and nonmetals are actually called semiconductors, and they're things that have some characteristics of metals and some characteristics of nonmetals. But we won't really talk too much about semiconductors tonight. They're not used as structural materials. The metals that we are mostly interested in when we're building aircraft are aluminum and iron, iron being the primary component of steels. There are various other metals that we get interested in from time to time, both as alloying agents and sometimes as materials that we use separately as structural materials. It's magnesium, which is even lighter than aluminum, titanium, chromium, nickel, copper, zinc, tin, and lead are the main ones I think that we get involved in building aircraft. As a generalization, by the way, hydrogen is up there, and it's being shown as a nonmetal, which seems a little weird because in normal periodic table, hydrogen sits way over on the left-hand side. And actually, hydrogen is technically a metal when it's in solid form, but it has to get god-awful cold to be in solid form. And normally it's a gas, and when it's a gas, it acts as a nonmetal. So we're classifying it as a nonmetal just for the sake of argument here. As a generalization, most metals are solids at room temperatures, and most nonmetals are liquid or gas at room temperatures. And there are some exceptions to that. Mercury, for example, is one of the few metals that is actually liquid at room temperature. And as I mentioned, hydrogen is sort of a metal, but it's gaseous at room temperature, doesn't really act like a metal. Metals are readily give up electrons. They tend to become positive ions, and they easily give up electrons. Nonmetals tend to be negative ions, and they readily accept electrons. And metals tend to conduct electricity, and nonmetals tend to be insulators or non-conductors. And as I said, the semiconductors that are right at the boundary between metals and nonmetals sort of have some of the characteristics of each. So if we think about a chunk of a pure metal, say iron or aluminum, but pure metal, we can think of them as an array of positive ions that they actually wind up being arranged in a kind of a regular crystalline structure. And we'll look at the crystalline structure in a minute. With a sea of electrons floating around that aren't very tightly bound to those ions and are free to float around, which is why the metals conduct electricity so well, because the electrons are free to move around. And if we apply a force to that metal, and again, this is a nice pure elemental metal of one of the metals on the periodic table, then that structure is fairly free to deform without coming apart. And that's what makes metal malleable, which means we can bend it, ductile, which means we can stretch it into a wire or something like that. And elemental metals, pure metals, tend to be malleable and ductile like that, and the reason is because of this structure. Now, if we want the metal to not be so malleable and ductile, if we want it to be harder, the usual way of doing that, or one way of doing that, is to alloy it, to add some other small amounts of other kinds of atoms to it, which results in a much more complicated structure that is less easy to deform. So pure metals tend to be pretty malleable, and we alloy those metals with impurities, either other trace metals or with non-metallic additives like carbon, and that makes the resulting material harder and more difficult to deform. We classify metals into two broad categories: ferrous metals and non-ferrous metals. Ferrous metals are simply ones that contain iron, and they're usually magnetic. Not always, like stainless steel isn't magnetic. It's considered to be ferrous metal because it's largely iron, but most ferrous metals are magnetic. And non-ferrous metals are simply ones that don't contain any iron, and they're typically non-magnetic, although, again, there are some exceptions. There are alnicomagnets, which are aluminum, nickel, and cobalt, and those are all non-ferrous metals, but when you put them together in the right combination, you can get them to be magnetic. But as just a general rule, ferrous metals are magnetic, and most non-ferrous metals are non-magnetic. If we look at the ferrous metals, it starts out with pure iron, which we can also call wrought iron. It's very soft. It's very malleable. It's easy to bend. And if we want it to be harder and less easy to bend, then the typical way is to add some carbon to it. And it doesn't take very much carbon to make a big difference in the characteristic of the metal. So there's a whole range of iron alloys called steels that are made by taking pure iron and adding a small amount of carbon. If it's a really small amount of carbon, less than 0.33% of carbon, it's called low carbon steel. If it's up to 0.7% of carbon, it's called medium carbon steel, and if it's up higher than 0.7, we call it high carbon steel. And each of those categories are progressively stronger and harder than the previous category. If we go crazy and add a whole bunch of carbon, we get something called cast iron. And don't ask me why cast iron isn't called very high carbon steel. I don't know why the terminology is like that. It doesn't make a lot of sense. And it's sort of really easy to confuse wrought iron, which basically is iron without any carbon in it, with cast iron, which is iron with a whole bunch of carbon in it. And they have radically different characteristics. Wrought iron is very soft and malleable. Cast iron is very hard and very brittle. For example, most lifters, tappets in aircraft engines, which have to be very, very hard indeed, are made of what's called chilled cast iron, and they're very, very high in carbon. And then there's something else, which I don't know why they call it steel. It's stainless steel, but it doesn't have any carbon in it. Stainless steel is kind of off in a whole different orbit than most steels, because it's not iron with carbon added. It's iron with a bunch of other things added, mostly chromium, and typically some nickel and maybe some molybdenum. But mostly chromium. And when you make an alloy out of iron with a bunch of chromium in it, it has very different characteristics from iron or steel. It's non-magnetic, it's highly corrosion resistant, and whereas all of these other things tend to be quite vulnerable to corrosion. When ferrous metals corrode, we call it rust. And stainless steel is very resistant to that. But it's, again, it seems to me cast iron really ought to be called very high carbon steel, and stainless steel shouldn't be called steel at all because it doesn't have carbon in it. But those are the terms that are used, so we just have to live with them. If we look at a stress strain diagram for wrought iron, mild steel, and high carbon steel, you can see how it reflects the different characteristics of these different alloys. The first thing that's most obvious is that as you add more carbon to the alloy, Young's modulus gets the material gets a lot stiffer, a lot harder. The slope of the proportional part of the curve gets steeper and steeper as you add more carbon, which means that the material becomes less and less flexible. But also the zone beyond the yield point, the plastic zone, becomes smaller and smaller as you add more carbon to the alloy. And what that basically means is that the material gets more and more brittle. It won't bend. The high carbon steel won't bend very much before it breaks. Once it gets beyond its, it's getting closer and closer to something like glass, where it's very hard and very strong, but it will fracture easily if you put too much stress on it. Whereas the softer alloy, say something like mild steel, will tend to bend rather than break, and we call that characteristic toughness. So there's a trade-off when you decide what alloy to use as to what's most important. Do you want this to be as hard as possible, or do you want it to be as tough as possible? And sometimes you want a combination of both, and we'll get into what we do when we need a combination of both, because sometimes we want material that's tough on the inside, but very, very hard on the outside, and there are ways of doing that. Going on to non-ferrous metals, we can break those down into two categories: the pure elemental metals, pure metals made of one element only: magnesium, aluminum, copper, zinc, tin, silver, gold, lead, mercury. Mercury isn't used very much as a structural metal because it's liquid, but I just threw it in there for completeness. And then there are some non-ferrous alloys that are combinations of these non-ferrous elemental metals that do not involve any iron, do not involve any carbon. And the most common ones are brass and bronze. Brass is copper with zinc. Bronze is copper with tin. There's also something called solder, which we use for electrical connections and stuff. That's an alloy of lead and tin. There's bearing material that we use called babbitt or white metal, which is an alloy of tin, antimony, and copper. So these are all non-ferrous metal alloys. Of all of these things, the ones that we are most concerned with in aircraft building are aluminum alloys. Commercially pure aluminum, that is aluminum that hasn't been alloyed with anything, is very soft and malleable and not very strong, and it isn't particularly useful. But aluminum becomes quite useful when we alloy it with some other metals to make it harder and stronger. And there are a number of different series of aluminum alloys. The 2000 series alloys, which are aluminum with a little bit of copper added, tend to be moderately strong and moderately tough, it's the most common kind of aluminum alloy that's used in aircraft structures. The most common is something called 2024 T3 alclad, which I'll talk about in a moment. There's also 6000 series aluminum alloys that have magnesium and silicon added, and those are much more corrosion resistant than other aluminum alloys, because most aluminum alloys are pretty vulnerable to corrosion. The 2000 series ones that we use mostly to build airplanes are quite vulnerable to corrosion. Then there's 7000 series, which has zinc added to it, and it's the strongest of all the aluminum alloys. But of course, being the strongest of all aluminum alloys, it's also pretty brittle. So we're limited as to what applications we can use it in. 6000 series are used pretty commonly in aircraft structures. The 6061 is a common alloy that's used in some wing spars and things like that. But 2024 is probably the most common alloy that's used in building aircraft. And I talked about 2024 T3 alclad. Let me decode that, because that's the most common material that we use, aluminum alloy that we use. The 2024 specifies the alloy, and you can go online and look up 2024 aluminum, and you'll get a specification sheet that shows exactly how much copper and tiny traces of other metals are added to the aluminum to make that alloy. T3 is a heat treating code. We're about to talk a little bit about heat treating, but heat treating is a process that's used to make the metal, to change the characteristics of the metal a little bit, and we'll talk about that in just a moment. And then the alclad means that the metal is, after it has been formed and heat treated, the exterior is plated with a very, very thin layer of pure aluminum. Typically 2024 T3 alclad sheet metal, which tends to be 20 thousandths, 32 thousandths, 40 thousandths thick, has a coating of pure aluminum on both sides that's about 1,000th of an inch thick. And it's there to protect the material against corrosion, because the 2024 alloy is very susceptible to corrosion. If it's exposed to moisture, it will corrode, because the aluminum and copper make a pretty active corrosion cell if there's an electrolyte added to the mix. Whereas pure aluminum, when it's exposed to air, turns into aluminum oxide, which is a very, very good protective layer. So the 2024 T3 alclad is coated on both sides with this very, very thin layer of pure aluminum to protect the alloy from corrosion. And it's very thin, so it's very easy to scratch and stuff. You got to be very careful with alclad, because the cladding is quite thin, and of course the pure aluminum cladding is also very, very soft. So it's fairly delicate stuff, and you've got to be careful with it. Let's talk a little bit about heat treating. Heat treating is kind of a magic thing, and I don't know how many of you got into aviation the way I did, building model airplanes, but my dad was a veteran model airplane builder. Back when he was involved, we built rubber band powered model airplanes, mostly out of balsa wood and stuff. Of course, we always had to put a landing gear on these airplanes, and the landing gear had to be durable enough to withstand some pretty terrible landings. So we would typically make the landing gear out of something called piano wire or music wire that you can buy down at a hobby shop, and it's spring steel wire. It's very springy, and it's just like perfect material for making landing gear on model airplane. The problem with piano wire or music wire is because it's so springy, it's very difficult to form it to the shape that you want, to make all these bends that you want when you're creating this landing gear. But it's got perfect characteristics for being a landing gear. It's just kind of hard to shape it into the shape you want it. So anybody who built these kinds of model airplanes learned that there's a trick to doing this, and the trick goes something like this. You start off with this real springy music wire, and you heat it up with a torch, and you heat it up until it's glowing cherry red, and then you allow it to cool slowly. And after it's cooled, the area that you heated cherry red and allowed to cool slowly becomes very soft and malleable and very easy to bend. The springiness is all gone. And when you bend it, it stays in the shape that you bend it to. It doesn't spring back, and it's just very easy to form to the exact shape that you want it. And the process of doing that is called annealing. And annealing is a process of using heat to make a metal softer. So we anneal this music wire. We shape it to the shape we want it. But of course, we can't leave it that way because we need to make it springy again. Otherwise, it's not going to be a very good landing gear. So the next step is that we heat that area that we just annealed and bent back up to cherry red. And this time, instead of letting it cool slowly, we cool it quickly by plunging it into a bucket of water. It's a process called quenching. And when we do that, when we heat it up to cherry red and then quench it in water and cool it down very suddenly, now that metal, instead of becoming soft, instead of being soft and malleable as it was after we annealed it, now becomes extremely hard and extremely brittle. And it would be in a pretty good state, for example, if we were making a knife blade, where we wanted it to be just as hard as it possibly could be. But it's not in a real good state for a landing gear because it's not springy. If one hard landing and the thing would snap because it's like I said, it's very hard, but it's very brittle, and we don't want the landing gear to be brittle. So then we take and this process of heating the metal up and then quenching it suddenly is called hardening, and it sure does. But that isn't really the state we want the metal in either. We want to restore it back to its nice springy state, the way it was when it came from the hobby shop. So then the last step of this process is we heat it up again with a torch, but this time we don't heat it nearly as hot. We heat it slowly until it gets to it turns blue, but we don't heat it enough for it to turn red. And we heat it up until it's blue. Then we allow it to cool slowly. And now all of a sudden, it turns out that this wire is now back in its nice, springy, tough state, perfect for being a landing gear, exactly the way we want it. And this step is called tempering. So the process, again, is to anneal first, which softens the material, then bend it to the shape we want it. Then we harden it by heating it and quenching it, and that makes it really hard, but it's too hard for the application. And then we temper it, which makes it just right, by heating it up not nearly as hot and allowing it to cool slowly. It's kind of like partially annealing it, if you will. So this is a good example of heat treating, where we use heat to vary the characteristics of the metal, to make it soft, to make it hard, to make it tough and springy, and by carrying out this series of heat treating operations, we can control its characteristics quite effectively. Now let's talk a little bit about why this works. Let's see, how are we doing here? And I'm going to get back in the weeds a little bit about this, but it turns out that iron, when it's at room temperature, assumes a crystalline structure that's called body-centered cubic, or BCC, where there are cubic crystals that have an iron molecule at each corner and an iron molecule in the center of the cube. and that's the crystalline structure of iron at room temperature. If we heat iron up to a high enough temperature, what's called a critical temperature, it's about 1400 degrees Fahrenheit, which just happens to be about the temperature that causes it to glow cherry red. The crystalline structure of the iron magically changes to something called face-centered cubic, where instead of having a molecule of iron in the middle of the cube, we have a molecule of iron in each face of the cube. Face-centered cubic has very different characteristics than normal iron. It becomes non-magnetic, for example. And it doesn't stay that way. Once we take the heat away, the iron goes back to being its normal body-centered cubic. So this is a state that the iron assumes only under high heat. Now, that's for pure iron. Imagine we have some steel, which is iron with a little bit of carbon added to it. When we heat the steel up above the critical temperature, the cherry red temperature, about 1400 degrees, and the iron transforms from body-centered cubic to face-centered cubic, there's no iron in the middle of the crystal, and carbon winds up migrating into the center of the crystal, into the center of these little crystalline cubes. And that forms a material that's called austenite, but it only exists when the steel is heated to cherry red temperature. It's not, austenite doesn't exist at room temperature. Now, if the austenite is allowed to cool slowly, then the iron atoms migrate back into the center of the cubes, and the carbon atoms come back out of the center of the cubes, and the result is a mixture of pure iron, it's called alpha iron, and a mixture and a compound of iron called iron carbide. And that mixture is a very soft material, very ductile material called perlite. On the other hand, if the austenite, which is cherry red, is allowed to cool very quickly, is cooled very quickly by quenching it, then there's not enough time for those carbon atoms to to migrate back outside of the crystals, and they get trapped inside. And the result is a crystalline structure called Martensite, which is very, very hard and very, very brittle. And here are some metallographs of these three different states: the austenite, which only exists at very high temperature; the Martensite, which is the very, very hard, brittle form; and the perlite, which is a mixture of iron and iron carbide. And you can kind of see what that looks like, and it's very soft. Now, the Martensite is which is what we get when we heat up steel into the austenite phase and then quench it very quickly. It's too hard and brittle to be particularly useful unless you happen to be making a knife blade. But it can be tempered by heating the metal back up to a lower temperature, somewhere between 200 degrees and 800 degrees, depending on what the final hardness desired is, and then cooling it slowly. This allows some of the trapped carbon atoms out, but not all of them. So it relieves some of that hardness and brittleness, but not all of it. And we can, by doing this hardening and then tempering, we can get the hardness versus toughness of the metal to the exact trade-off where we want. You can think of, as I mentioned, you can think of tempering as partial annealing, where we do the hardening to get it extremely hard, and then we partially anneal it to soften it back to the characteristic that we want. And it's always a trade-off. The harder the metal is, the more brittle it becomes, the less tough it becomes. And so we're trying to get that magic balance between hardness and toughness that we want for a particular application. Aluminum alloys also can be hardened through heat treating and softened by annealing. I won't go into all of the chemistry and stuff of how that works, but it's very, very similar in principle to how it worked with steel. The critical temperature of aluminum is a lot lower. It's about 800 degrees Fahrenheit, not 1600, not 1400 degrees, but the basic principle of how heat treating and annealing works for aluminum alloys is pretty much the same. In addition to heat treating, there are some other things that we can do to change the hardness of metal. We can do something called strain hardening. Basically, strain hardening means that if we take metal and we forcibly compress it, it becomes harder. And there are various processes for doing this. We can use cold rolling, which is one of the processes that's used in making 2024 T3 aluminum. We can do something called shot peening, where we shoot little hard metal pellets at the surface and create a whole bunch of little tiny dimples. Typically, something like a connecting rod is hardened by shot peening. A real good example of strain hardening is the humble aluminum rivet, AD rivet, where it starts off pretty soft, but when we drive the rivet with a rivet gun, we're basically strain hardening the rivet, and so it becomes a permanent joint. The rivet is much harder after we've driven it than it was when it came out of the box. Again, because we're putting the material under compression and squeezing the atoms in the crystalline structure closer together in a way where they remain permanently deformed in that state. Another more spectacular way of strain hardening is called forging, where we heat up a piece of metal to a high temperature, and then we put it in a hydraulic press and slam a whole lot of pressure on it. And a lot of the really hard things, the highest stress components like connecting rods in our engines and some pistons are made by forging. And again, this is a form of strain hardening where we're putting a lot of pressure on the metal in a compressive way in order to make it harder. Now, sometimes we don't want to make the whole part harder. We just want to make the surface harder. Here's a perfect example or gears, where if we'd like the surface of the gear to be as hard as we possibly can, so it has really good wear characteristics. But if we made the whole gear that hard, it would be vulnerable to fatigue fracturing, because the harder the metal is, the more brittle it is. And so we really want the inside of the gear to be tough and the outside, the wear surface of the gear, the very outer layer, to be very hard. And the same thing is true of lots of other components like camshafts and crankshaft journals and stuff. And the process of hardening just the surface of the part is called case hardening. And there are a number of different ways to do it. We've already mentioned some of them. We can harden the surface of a material by rolling or shot peening. We can heat treat just the surface of the metal by using induction heating, where the material goes inside of some coils and some high energy AC is applied to them that heats up the very outside. Or we can use chemical case hardening. And most crankshafts and camshafts are case hardened chemically by a process. Well, most camshafts are hardened using a process called carburizing. Carburizing is a process where a steel part is put in an oven and heated up to a pretty high temperature in an atmosphere of carbon monoxide. And it's baked in a carbon monoxide atmosphere for a few hours. And during that baking period, the carbon in the carbon monoxide starts diffusing into the surface of the steel, turning the very surface into a much higher carbon steel than the rest of the part. And if you recall, the higher the carbon, the harder but more brittle the material is. So you start with a mild or medium steel, probably a medium steel, and then you cook it in carbon monoxide, and the surface develops this high carbon steel outer shell or outer case that's considerably harder than the interior. And typically, when you carburize a camshaft, the hardened layer is maybe 15 thousandths of an inch thick, but it provides a very, very durable wear surface where we're interested in maximum hardness. The same sort of thing is done on crankshafts, where we want the journals, the polished parts that the bearings run on, to be as hard as possible. Most crankshafts are case hardened using another process called nitriding, which is very similar to carburizing, except that the part, instead of being baked in a carbon monoxide atmosphere, is baked in an ammonia gas atmosphere. And during that baking process, the nitrogen winds up diffusing into the outer surface and creating a very hard outer surface that's 10 or 20 thousandths of an inch thick. So these are all ways of case hardening material. So we have all of these tricks for making metal do have just the characteristics we want. We can alloy it, we can heat treat it, we can strain harden it, we can case harden it, and the result is that we can just do some pretty amazing things with making metal have just the characteristics that we want. It's amazing what we can coax metal into doing through all of these techniques. I find it kind of fascinating stuff, and I hope you did too. Tim, that's all that I have right now, but if we have a little bit of time left, we can open it up for some Q&A.
Okay, Mike, great. Yeah, we have a few questions that have come in already, so let's go ahead and jump in with them. Tom is wondering if you could discuss pros and cons of chrome versus nitride cylinders.
Sure. And there's actually a couple other competitors, because we also have nickel plated cylinders nowadays, or nickel carbide plated cylinders. The advantage of chrome plating cylinders is twofold. The one is that chrome is very, very corrosion resistant. So if you're operating an airplane where the operation is very seasonal and it sits around a lot, or if you're operating an aircraft in a very high corrosion environment like South Florida or something, where the cylinders are under a lot of corrosive attack because of the environment, or if they have both characteristics, like, probably the most extreme case would be like a seawater seaplane, that typically is a pretty seasonal operation and also lives in the world's worst corrosion environment. Then chrome it has a lot of advantages because it won't rust, it won't corrode. It also is very, very hard, so it wears well. The biggest disadvantage of chrome plated cylinders is that they are very hard to break in, and they use a lot of oil. They use a lot more oil than a steel cylinder would. Now, that's not necessarily a terrible thing, but most pilots don't like their airplanes to use a lot of oil, and it's simply the nature of the beast with chrome cylinders. They use a substantially larger amount of oil than a comparable steel cylinder would, and they're tough to break in. A chrome cylinder can take the better part of 100 hours to break in, whereas a steel cylinder, if you do it right, can be broken in 5 hours. The more recent advent of nickel carbide plated cylinders, I think, represents a really good third option, because the nickel plating is also very corrosion resistant, and nickel carbide cylinders break in extremely quickly and use very little oil. And so the nickel carbide plating process has significantly made significant inroads into the chrome plated cylinder business, because it really represents kind of the best of both worlds between a nitrided steel and chrome plating. So I think that's probably most of what I can say on that subject.
Okay, Roger's asking, it would seem that any scratch on 2024 Alclad could be serious. How does one deal with that?
2 words: primer, paint. If you have a polished aluminum airplane, you don't want to put paint on it. You have to be very, very careful, because, as I said, the Alclad is very thin and very soft, very easy to scratch. That's why most of our airplanes are painted, and we have very, very good polymer paints now that do a very good job of protecting the surface. But Alclad is quite fragile. Also, anytime the cladding is punctured, let's say by drilling a hole for a rivet, you create a place where the sheet metal is subject to corrosion, because it's no longer protected. And an awful lot of the corrosion problems that we have in aluminum airplanes originate at rivets for that reason, because the alcladding, by definition, the cladding has to be punctured in order to drive the rivet in there. So, but basically the answer is paint. And on the inside, at least put some sort of a corrosion resistance primer on it. The Cessnas that were built before 1976, when they 1986, when they shut down the production line in Wichita, almost all were built with no internal corrosion proofing. If you look inside the tail cone of a single engine Cessna that was built prior to 1986, you'll just see shiny aluminum in there. And it might not be so shiny anymore. Whereas the comparable airplanes, say Beach Bonanza or something like that, if you look inside the tail cone, you'll see it's all been coated with zinc chromate primer, which was the primer du jour back in those days. If you look in the tail cone of a Cessna that was built after they restarted production in Independence, Kansas, in whenever it was 94, I guess it was, you'll see that every piece of sheet metal on that airplane is coated with an epoxy primer inside and out. There's no bare metal whatsoever in what we call the restart Cessnas that were built from 1994 on at the Independence plant. So Cessna kind of learned their lesson. When Cessnas were built originally, nobody expected anybody would keep them for more than 10 years. They were built as like throwaway airplanes. And Cessna learned its lesson in in the 10 years that they were not building single engine airplanes. They transformed from building the least well corrosion protected airplanes to the most corrosion protected airplanes in the business. And the way they did that was every piece of sheet metal before it gets riveted on the airplane gets dunked in a tank of epoxy primer. So everything's protected.
Bart is asking, why wouldn't aircraft use more of 6061 alloy versus the 2024? You would think more corrosion resistance would be preferable versus delicate alclad.
6061 is not as flexible. It's not as easy to form. It's more brittle. And my own experience is that 6061 is primarily used in high strength applications like spar caps and stuff, but is not used very often in run of the mill structure and in skins and stuff like that.
And Gordon's wondering, can you talk a bit about dissimilar metals and the importance of using the right fasteners?
I can a little bit. Most of the airplane manufacturers did a pretty good job of being sensitive to that. Dissimilar metals corrosion is where we put two dissimilar metals together in a way where they can form a corrosion cell. I know that there have been some issues with some of the Piper products where they used some steel angle reinforcements that were riveted to aluminum structure, and that developed some pretty serious corrosion problems. We see a lot of issues with people who buy airplanes and quickly change all of the cadmium plated screws to stainless steel screws because they look pretty, and then discover that the stainless steel screws have galled and you can't get them out. And drilling out stainless steel screws are really hard because stainless steel is so hard. It's very hard to get a drill bit to drill them out. I was one of those aircraft owners when I first became an aircraft owner. Didn't really know very much about this stuff. I bought a stainless steel screw kit and replaced everything with stainless steel screws to make it all pretty looking, and then discovered the hard way that wasn't such a good idea. Now pretty much all of the screws have gone back to being CAD plated steel screws. Typically, when we use steel fasteners on aluminum aircraft, those fasteners are cadmium plated, and the cadmium plating it eliminates the dissimilar metal problem because cadmium is compatible with aluminum, whereas iron is not compatible with aluminum. Iron next to aluminum creates a pretty bad corrosion situation. But if you have cadmium plated screws and you don't and the cadmium plating is in good shape, then you don't have any corrosion problems. And it's usually a pretty good idea not to reuse CAD plated screws too many times, because every time you take them out and put them back in, some of the cadmium plating is rubbed off. And if the cadmium plating is breached and you wind up with steel against aluminum, then you can have corrosion issues. I don't know whether I answered the question or not, but it is a problem. You need to be sensitive to it. And I mentioned a couple of the cases where I've personally run into dissimilar metals corrosion.
Okay. Tom's wondering what is meant by chrome moly tubing.
Well, that's a good question. I'd have to look up the material specifications, but it's a steel tubing that's alloyed with chromium and molybdenum, and the chromium gives it good anti-corrosion characteristics, and I'm not sure exactly what the molybdenum does, but I would have to research that. I'm not a metallurgist, although I play one on TV from time to time.
Yeah, well, you did a good job of it tonight. Very informative.
I try to make it accessible because it is a pretty complicated subject.
It is. It was kind of like an advanced level of instruction I think you gave us tonight.
Oh, did you learn anything?
Oh yeah. Joe was wondering, can you talk a little bit about Aladyne?
Yeah, Aladyne, which actually I was interesting. I read a press release that Aladyne is no longer called Aladyne. The company that makes Aladyne just changed its name, which I can't believe because everybody's called it Aladyne for forever, and it's probably kind of confusing. But Aladyne is a it's called a conversion coating, and it's used on aluminum prior to priming and painting as a corrosion inhibitor, it chemically combines, I think, with the aluminum cladding probably to cause it to oxidize and turn into aluminum oxide more quickly and become a stronger and more effective corrosion barrier than the pure aluminum that is put on there at the factory. So the normal procedure is after you put something together that involves aluminum, particularly aluminum sheet metal, you Aladyne it. You apply this stuff, you leave it on for a certain period of time, you wash it off, then you put primer on it, and then after the primer, you paint it.
Okay, that leads to Keith's question. In a low humidity environment, can I just Aladyne treat my aluminum wing spars rather than prime and paint, like on the gold-colored hardware?
You can. Sure. It's just... how sure are we that this airplane's always going to live in a low humidity environment? That's the question. But yeah, I mean, if the airplane's based in Tucson or Denver or something like that, it's not at very much risk of corrosion. If it winds up moving to Santa Barbara, then all bets are off.
David's wondering, should we wet install rivets when building our own metal aircraft to prevent corrosion?
Well, I know that's sometimes done. It's really, I mean, it really depends on the materials involved. If you are using aluminum AD rivets to rivet together aluminum structure, there's really not, not a significant risk. And once you put it together, just if you apply some primer, it will pretty well protect it. In the case where you're using dissimilar metals, for example, steel fasteners on aluminum structure, then you have to do some fairly exotic things to protect the joint against dissimilar metals corrosion.
Okay. Keith is wondering, does the annealing, hardening, and tempering process work with alloys of aluminum also?
Yes, it does. As I said, it's done at lower temperatures than the ones we were talking about with steel, but it absolutely does. And aluminum is routinely heat treated. As I mentioned, the most common material that we use in aircraft structure is 2024 T3 Alclad, and the T3 is the code that talks about both the heat treat and the cold rolling, both of which are designed to harden the material.
And James is wondering, is tempering the same as normalizing?
Normalizing is a, I believe normalizing is a term for tempering a material back to its original state. So normalizing is a particular kind of tempering where we mentioned that using tempering you can bring the material to a wide range of different trade-offs between hardness and toughness. Normalizing refers to tempering something back to its original condition. So, for example, after welding, for example, if you wind up welding something, it screws up the heat treat, and then you need to normalize it to get it back to the way it was before you welded it.
Walt's wondering, does shot peening only affect the surface skin of a metal structure?
Yes, that's what it's for, is to compress the very outer layer of the structure to case harden the material.
And David's wondering, what is hydrogen embrittlement, and are aluminum alloys subject to hydrogen embrittlement?
Well, now you're getting to the very edge of my knowledge. I've only heard of hydrogen embrittlement in the context of steel. I'm not sure whether aluminum is subject to hydrogen embrittlement or not. I'd have to research that. But hydrogen embrittlement is a process where a material, usually due to some contaminant when the metal was alloyed, winds up becoming harder and more brittle than it was originally designed to do. For example, we had a rash of failures of through bolt nuts on Continental engines. The Continental engines use through bolts to hold the case halves together and hold the cylinders on, and they have very special nuts because they're torqued to an extremely high torque value, and they're 8-point nuts, and we wound up having a rash of these 8-point nuts that wound up splitting and falling off the through bolts because they wound up being too brittle, and they fractured under stress. And the diagnosis of why they did that was hydrogen embrittlement. And as far as we can tell, it was just a bad run of these nuts that came from the supplier, and the metal was too hard and too brittle for the application, and so the nuts wound up fracturing.
And Paul's wondering, what is anodizing, and how can I use that process for corrosion prevention?
Anodizing is something that is done with aluminum, and it's I don't know the precise details, but it involves taking a piece of aluminum and putting it in a chemical bath attached to an electric current, which causes a formation of a protective layer on the outside. It's an alternative to cladding. It's another way of protecting aluminum alloy with a coating over it, a metallic coating that is a lot less susceptible to corrosion than the structural alloy is. And I wish I could be more specific about the details, but I would have to. I think I knew more about about anodizing at one point, but it just seems the details seem to have escaped me, so I can't answer in more detail than that.
Charles is asking, is there a corrosion-resistant treatment for camshaft surfaces?
Oh, we wish there was. I kidded a while back with Jimmy Tubbs, who was the long-standing engineering vice president of ECI, and who pretty much pioneered the process of nickel carbide coating of aircraft cylinders. And I'd said to Jimmy, if you could figure out a way to put that stuff on camshafts, you'd really have something, because camshaft corrosion is a real serious problem, and it's one of the main reasons that engines don't make TBO. But as far as I can tell, nobody has yet come up with a process for building a camshaft that's hard enough and also corrosion resistant. There are some really exotic processes that have been developed in recent years. I know of some that have been used on automobile racing engines. They're very exotic and very expensive, and I think there may be some hope that eventually those processes become available in our aircraft engines to create camshafts that are camshafts and tappets that are less vulnerable to corrosion. But so far we don't have any that are commercially feasible.
Michael's wondering, what are your thoughts on treating unprimed interior metal with ACF 50 or Corrosion X as a means of corrosion prevention?
I like those corrosion treatments very much. I've used them in my own airplane. Their big advantage is that you can apply them in areas that simply are inaccessible to paint, because they're applied at very high pressure, and they create a fog, literally, of ultra tiny droplets that just kind of float around and get into all kinds of nooks and crannies of structure that normally would be inaccessible. And they form a one molecule thick hydrophobic layer that prevents corrosion very effectively. The problem is that those treatments don't last very long, and you have to retreat every couple of years. It's not a one-time thing the way, say, priming or painting would be. So the advantage is that you can get it into areas where you can't practically prime or paint. But the disadvantage is you have to redo it every few years.
Four is asking, I've seen some A&P mechanics anneal spark plug washers between the plug and the cylinder every time they remove spark plugs for the 100-hour or annuals, while others, A&Ps, never do anything to the washers other than possibly flipping them over from their original position. Any suggestions, pro or con?
Oh, yeah. Well, first of all, I'm of the camp that thinks it's kind of silly to anneal spark plug washers, because they're very, very cheap. And you buy them in boxes of 100. I personally never, ever reuse a spark plug gasket. But because like I say, they're dirt cheap and they come in boxes of 100, they don't cost very much money, and there's no really compelling reason to ever reuse them. But if you do reuse them, you really must anneal them, because the spark plug gasket work hardens in service, and is no longer soft enough to provide a good seal if you reuse it unless you anneal it. And annealing again is heating it up hot with a torch and then letting it cool down, because because the copper gasket is pretty much chemically pure copper. It's not alloyed with anything. It really doesn't matter whether you cool it down slowly or quench it. All you need to do is heat it to critical temperature and then cool it down one way or another, and it becomes annealed. But you either have to throw it away and use a new gasket, which is what I do, or you need to anneal it. You can't just reuse spark plug gaskets in the state that they came off the engine. And you definitely don't want to turn them over either, because spark plug gaskets are asymmetrical and there's a correct way for them to go and a backwards way for them to go. So you definitely don't want to flip them over. So my first choice is to not reuse them and put new ones in each time. The second choice is to anneal them.
So this leads us to Darren's question. Do engine parts get unintentionally tempered?
Well, hopefully not. Hopefully they don't get hot enough for that to happen. If an engine part is operated outside of its design temperature limits, for give you a perfect example, if a cylinder goes into pre-ignition, for example, and in pre-ignition we see cylinder head temperatures go from their normal values, which are typically in the 300 degrees to say 400 or 420. And in a pre-ignition case, the temperature will often go up to 600 or 650 degrees very, very quickly, because pre-ignition is pretty violent. And it'll typically go up on the order of 1 degree Fahrenheit per second. So it goes up very, very quickly. A cylinder that has undergone that kind of heat abuse probably should simply be junked, because even if the piston is definitely going to be junked because it's going to be melted, but if the cylinder head might still look okay, but if the cylinder head temperature got up that high, I personally wouldn't reuse the cylinder, because the cylinder has grossly exceeded its design temperatures, and the heat treat of the cylinder could be very adversely affected. It's not very common for engine parts to operate significantly outside of their design temperature envelope, but that's one case that I can think of that where it happens from time to time. It's pre-ignition events which cook cylinders way, way hotter than they were ever designed to be.
Interesting stuff, Mike. Hey, let's wrap it up here. Please take a moment and share any closing thoughts you want with everybody. We had a great turnout tonight, over 650.
Oh, wow.
According to my counter. So
that's great. I'm very, very pleased to hear that. Well, the usual stuff. If you're not on my email list for my monthly newsletter, you can put yourself on the list by going to savvyaviation.com and clicking the little red button at the very top of the screen that says get on the newsletter list or something. Or if you stick around and take the post-webinar survey that Tim's going to put up, there's a little checkbox on the survey you can check that says you'd like to be on the mailing list. My book manifesto is available at Amazon, and I am making great progress on the engine book. For those of you who are interested, we are going to have the engine book ready for AirVenture this year, and we're working really hard. We're going to finish all of the editing by the end of this month. And the page layout is supposed to be all done by the end of May. And so we're working hard to get this book available for AirVenture. It's going to be a big one. It's I don't have an exact page count yet, but it's I believe it's got something like 50 chapters in it. So it's going to be a big book. But I'm excited about that. If you want to be involved in the production of this book, you can still go to my Patreon page and sign up and get an advance copy, get one of the first copies of the book when it becomes available. And finally, just want to review the next few first Wednesday of the month webinars that I'll be doing in April. The webinar is called Don't Shoot Yourself in the Foot. We'll be talking about things that aircraft owners do to torpedo the maintenance of their airplanes. May 2nd, the webinar is called Where Fuel Meets Air. We'll be talking about the various mechanisms in aircraft engines that meter fuel into the induction air, carburetors, pressure carburetors, fuel injection systems, stuff like that. And in June, the webinar is titled Planes versus Cars, and we'll be talking about some of the differences between planes and cars, the cost differences, the longevity differences, why planes have TBOs and cars don't, and a whole bunch of interesting stuff comparing planes and automobiles. And so that's all I have, Tim, and be looking forward to seeing everybody same time, same station next month.
Hey, that's great, Mike. It looks like you got a great lineup coming here. Looking forward to the upcoming webinars that you have. First Wednesday of the month, 8 p.m. Central Time. Thanks again, Mike, for joining us tonight, sharing your information. Very informative, very interesting stuff. Thank you so much for sharing.
My pleasure.
To everybody who tuned in tonight, thank you so much for joining us. Have a great night, everyone. Hope you can tune in next week.
Good night, everybody.